Hi students, welcome to 165 GTS Chemistry Classes. This is JAYARAM, your chemistry faculty. In previous class, we discussed about the structure of glucose. In biomolecules part, we are discussing the carbohydrates, and in that carbohydrates, in the first class we discussed about the classification, and next class we discussed about the structure of glucose, because all the remaining carbohydrate structures we can derive only with respect to glucose structure. That's why with how the glucose structure has been established, that is nothing but the elucidation of glucose structure we discussed in previous class. Clear? And with a review of that glucose structure with a different experimental result, what is the structure given to glucose, and thereafter what are the questions which are unanswered from that structure, thereby in continuation to that what are the developments. All these we have to discuss. Clear? And in this class let me give the structure of a briefing on the structure of the glucose. That is nothing but from the experimental result, glucose is found to have one aldehyde group, and then it is of having 5 hydroxy groups, but out of these 5, that is hydroxy group means they are nothing but alcoholic groups. Yes, and out of these 5 alcoholic groups, one is primary alcoholic group, the remaining 4 are secondary alcoholic groups, and from the experiment, that is with the result of the reaction of glucose with HI in presence of red phosphorus, we understand that all these 6 carbons in glucose are present in straight chain like this. This is the structure given by Bayer. Bayer proposed this structure, open chain structure. Clear? And it is nothing but from the experimental results or inferences. He is proposing this structure. Now, with this structure, so many questions answered, no doubt at all. But still, unanswered questions are there. What are those? They are nothing but when this glucose is reacting with Tollens reagent, Pelling solution, and Benedict solution, which are nothing but only aldehydes can respond with that. That is this group. Why it is not responding to Schiff's reagent? Schiff's reagents are nothing but imines. Just you remember, Schiff's bases or reagents are nothing but imine. Imine is nothing but double bonded nitrogen like this. Here hydrogen may present or some other alkyl group may present. These imines are. Why glucose is not responding to Schiff's reagent? One. And the second one is it is not responding to sodium bisulfite NaHSO3, where in carbonyl compounds, if you remember that aldehydes and ketones, that is carbonyl compounds can respond to sodium bisulfite. Orange color crystal salts will be formed, water soluble salts. Yes, but here when it is aldehyde, because Tollens reagent is responding, why it is not reacting with this NaHSO3? And one more is it is also not reacting with ammonia. And then one more question which is not answered is why there is mutarotation. Mutarotation. Just we have to start with this one. A review on this one. Mutation nothing but sudden change or altogether change in the regular characteristic features which is quite deviating from its regular characters is nothing but mutation. Here mutarotation. Mutarotation is nothing but that is specific rotation. Already we discussed about this optical isomerism. In that optical isomerism, some compounds are able to rotate the plane polarized light in clockwise, then it is dextrorotatory. In anti-clockwise some compounds, then it is laborotatory, and that rotating nature is known as optical activity. That optical activity is measured in terms of specific rotation. Now that specific rotation of glucose when dissolved in water is changed. That is, always we can find that change. Actually, when it is dissolved in water, its specific rotation is changing from certain value to a fixed value. Such change in specific rotation is known as mutation. Now, for these questions, answers are not obtained from this structure. And first of all, let us have a discussion on this rotation. And rotation is nothing but actually, even though already I think it is in previous class we discussed, even though this glucose is proposed this open chain structure like this with aldehyde group and 4 secondary hydroxy groups or alcoholic groups and 1 primary alcoholic group. Out of these, the fifth carbon, this is fifth carbon because it is 1, 2, 3, 4, 5 and this is sixth carbon. You have to remember. This fifth carbon alcohol is attacking on this carbonyl group. And where what we are expecting in previous class? Yes, it is giving when this aldehyde group, actually it is having the structure like this. Oxygen with double bond. This is nothing but sp2 hybridized carbon. Once it is sp2 hybridized, it is planar. And when OH is attacking, it can attack on both sides. So with one vision, that is, if it is attacking on one side, if it is getting this OH on right side and the hydrogen on left side, this is, and here just what I am giving is the open chain structure slowly getting into close, and when it is close, this is here we are giving the structure like this, but just you remember here in bend there is no carbon. It is for our convenience sake, for cyclic form we are writing like that. Only the carbons, here this carbon and fourth carbon, third carbon, second carbon. Here the groups are as usual. In this case, what we are observing, this is the fifth carbon, is it not? In fourth carbon and in third carbon, there is no change in the configuration or in the structure. This is. Altogether here what happens is, the aldehyde group, first carbon, is now with OH group as well as OR group. Nothing but semi-acetal. If you remember that alcohols when react with carbonyl compounds in basic media, they are forming alkoxyphenols. Alpha alkoxy, this is carbon, OH group, this is OR group. That alpha alkoxy alcohols are known as semi-acetals or hemiacetals. Here this semi-acetal or hemiacetal is formed, but it is in cyclic way. That's why cyclic semi-acetal is formed. Now it is one of the assumption that OH is going on right side. Now with the same assumption, if the so-called OH is going on left side, this is carbon, OH is on left side, and here hydrogen, and as usual this is straight chain with CH2OH, and then the structure we are writing is from this to fifth carbon, here hydrogen and fourth carbon, third carbon, second carbon, no change in their structures, like this they are appearing. It is like this, OH and H, OH and OH, H. This is, it is appearing like this. Now you can observe that this is first carbon, second, third, fourth, fifth and sixth carbon. Now, in these two possibilities, this is when this open chain is converting into cyclic semi-acetone, depending on the position or the direction of OH group from the fifth carbon attacking of this carbonate group, OH may shifted to right side or left side. If you observe, all the remaining except on carbon 1 here, except in carbon 1, OH left side, OH right side. In all the remaining cases, in all the remaining carbons, there is no variation. Clear? Here in last class, what I introduced the word is such type of different forms of the same carbohydrates which differ at C1 configuration. You remember, only at C1 configuration are known as anomers. These are known as anomers. And just you remember, carbohydrates sometimes they differ at other than C1 configuration. Say for example here these two are glucose, and in these two glucose forms OH is differed only at, that is the configuration is differed only at C1 first carbon. But if it is at other than first carbon, then they are not the forms of the same compound. Just try to understand my point, dear students. Here you concentrate. These two forms which are differed in their configuration at C1 belong to the same compound, that is same carbohydrate. Here it is D-glucose. Why D-glucose again? This is no doubt at all D-glucose. Can you confirm? Can you consider what is the fact to consider this as D-glucose? Yes, it is because on last but one carbon OH is on right side. Then it belongs to D series as per DL notations. So in this D-glucose, when this fifth carbon OH attacks on that, the two forms are formed for D-glucose. Such two forms of the same carbohydrate which differ at C1 configuration are known as anomers. Just you remember, first carbon, first letter. If they are differing at other than C1 configuration, just you remember, then they are not the forms of the same carbohydrate. They are different carbohydrates. They are different carbohydrates. Say for example, if any carbohydrate with the same molecular formula is differing in their configuration at C2 or C3 or C4 compared to glucose, then such carbohydrates are known as apimers. Apimers. Just you remember, apimers are different carbohydrates that differ at a particular carbon. Now these apimers, they may be, depending on the carbon where the configuration differs, they may be C2 apimers, or they may be C3 apimers, or it may be C4 apimers. Clear? And let me give, for instance, you just when we are discussing this, you remember this one. Let me give the examples for this. This C2 epimer. Mannose is C2 epimer of glucose. Mannose, glucose. And just you remember, always this epimerism or this anomerism. Anomerism is individual. For every carbohydrate, alpha and beta forms are automatically anomers. But epimers, it is always with reference to glucose. So mannose is C2 epimer. And allose, one more compound. It is nothing but ALLOSE. Allose is C3 epimer of glucose. And now coming to C4 epimer. For C4 epimer with glucose is galactose. Galactose is C4 epimer with glucose. So for your convenience sake, I am giving all these. Mannose C2 epimer, allose C3 epimer, and galactose C4 epimer. That means mannose and glucose different carbohydrates. but they are having the similar structure except at C2. Here in glucose on carbon 2, OH is on right side. If it is on left side, it is mannose. And similarly at C3, H is on right side, OH is on left side in glucose. If it is reverse, then it is allose. Like that. I think you got my point. So at C1, now all these compounds, that is mannose, allose, galactose, they are having two forms, no doubt at all. One is alpha form, another one is beta form. Alpha D mannose, beta D mannose. Those two are anomers, anomers of mannose. Similarly, alpha D allose, beta D allose are anomers. Alpha D galactose, beta D galactose are also anomers. And just you remember, there is no relation between alpha form of one carbohydrate with the alpha form or beta form of the other carbohydrate. Because alpha beta forms are the forms of the same carbohydrate. You have to remember forever. And when it is coming to epimer, they are different carbohydrates. And in each carbohydrate, there is variation in C1 configuration. Those two forms of the same carbohydrate which differ at C1 configuration are said to be alpha and beta forms of that particular carbohydrate. Clear? That is epimers, anomers. Every carbohydrate has anomer, anomeric form. That is, every carbohydrate can exist in alpha and beta forms. Yes. Now your question is, what about fructose? Fructose is not epimer. Yes, fructose, which is, this is nothing but aldohexose. Is it not? Why it is aldohexose? Can you count? Why it is aldohexose? Aldo because of aldehyde group. Hexose because of 6 carbons. Now fructose, here I am writing fructose is having the same molecular formula. This is fructose is having the same molecular formula C6H12O6 and hence it is also hexose. But here the structure of fructose appears like this: CH2OH C double bond O and then CH2OH and here 1, 2, 3. This is OH, H, OH, H and here H, OH. Now if you observe on this is, let me give the number of carbon. It is 1, 2, 3, 4, 5, 6 carbons. But unlike that of glucose, here the functional group is keto group and hence fructose is ketohexose. What is fructose? It is ketohexose, whereas glucose is aldohexose. Now when one is keto and the other one is aldo, what is the relation? Yes, they are, that is fructose and glucose are functional group isomers. They are not anomers, they are not epimers. Just because of having different function group, main function group different and hence they are functional group isomers. Are you clear? So altogether with this one, anomers are the two forms of a carbohydrate. And then epimers, two different carbohydrates that differ at other than C1 configuration. That is, it may be of having different configuration at C2, C3, C4. Best example is this. And depending on the difference in the configuration at a particular carbon, they are said to be with the number of that carbon, C2 epimer, C3 epimer, C4 epimer. These are the examples. And now coming to fructose, fructose is not epimer. Fructose it itself is of having a different functional group. And hence, glucose and fructose are functional group isomers. Clear? And now, when it is glucose, one is OH on right side, one with OH on left side on C1 carbon. Just you remember, in all these carbohydrates also, when two forms exist, the form in which at C1 OH is on right side is said to be alpha form. This is glucose and hence this is alpha D glucose. Here alpha indicates the anomeric nature, D indicates this last but one carbon OH orientation, and it is glucose. And now what about when it is on OH is on left side, it is known as beta D glucose. This is beta D glucose. Clear? Okay. Now we are considering two forms of carbohydrate, particularly when we are discussing a specific study of glucose, it has two forms. Now let me write these two forms, alpha D glucose and the other one is beta D glucose. And how we can consider these two forms? Just you remember, when glucose is crystallized from the sugarcane juice at 30 degrees of centigrade, the crystallized form is alpha D glucose, and it is of having a boiling point of 146 degrees centigrade. And one more characteristic feature here is its specific rotation, and just you remember specific rotation is symbol with alpha D. This specific rotation is plus 111 degrees. Dextrorated. Now coming to beta form. Beta D glucose. It is crystallized at 90 degrees centigrade. Crystallized from concentrated solution at 90 degrees centigrade. And its boiling point is 150 degrees centigrade. And its optical rotation, that is nothing but specific rotation, is found to be 19.2 plus 19.2 degrees. Totally alpha form, beta form, both these two are dextrorotated, but one is with 111 degrees of angle of rotation and the other one is only just 19.2 degrees of angle of rotation. Clear? And now these two forms are formed from the open glucose like this. And just here you follow, when this open chain glucose is converting into alpha and beta forms, just you remember those alpha and beta forms of glucose are establishing an equilibrium among these three. Here this is OH and here H. Now when it is converted to alpha form is nothing but C, first carbon OH on right side, and this is like this CH2 OH H OH H H OH, and this is second carbon OH H, and this is hydrogen 1 C1. And if it is converting into beta form,